we're just going to be looking at some applications. So we're going to look at some real life situations that can be described using exponential or logarithmic equations. The first of those situations is going to be regarding sound intensity. So sound intensity as measured in decibels can be described by the equation B equals 10 times log of I over I naught, where that B, that's actually the Greek letter beta, is the number of decibels. I is the sound intensity in watts per meter squared, and I naught is a constant. You guys familiar with measuring sound in decibels?
Yes.
Sports fans?
Yes.
What do you notice on the big game?
Yeah, it just the more louder.
They got the sound meter going, right?
The louder, the more.
Yeah.
Sure.
Where it's like, hey Jim, it's really loud down there. Sounds like a jet taking off. And then Jim's like, what? No?
Nope.
Okay. That's my Tony Romo impersonation.
Do you care if I play chips?
You can snack on some chips. Just try not to do too much rustling on me.
You classify those as chips, don't you? I mean,
You get it open and just like easy on the rustles.
okay.
Deal?
I think you just call it what they are. You have no lunch either.
All right.
You're chewing the thing at that.
So example time, given that the sound intensity of a busy city traffic is approximately 10 to the negative fifth watts per meter squared. That's our I. What is the measure of the city traffic in decibels? So we're looking for beta. So we'll just plug this stuff in to our formula. Is everybody okay with where I plug things in? All right, participation. How do I simplify 10 to the negative fifth divided by 10 to the negative 12th?
You want to subtract the
Great, we subtract the exponents. Negative 5 divided by, negative 5 minus negative 12 is? Nope.
negative 7.
Nope. 7.
Oh, yeah.
Wow. Is that it?
No.
Oh.
Okay.
Alright.
So when we write log, write that, just log with no subscript. What is the base of that logarithm? Great. And then what can we say about log base 10 and exponent base 10?
I think it's low.
Yep.
Wow.
Good.
You're like so smart.
So that's 70 decibels.
That's all the test will be, right?
Or you could have just at the initial step, just typed in your calculator, right? Like the initial formula.
So,
But, yeah, what's
if
up?
I'm at a football game and I want to like measure the decibels.
Yeah.
How will I like do that?
What kind of instrumentation you use to measure decibels?
But they have a decimal figure.
You can't just listen to it.
Well, what's going to happen is you're going to have some kind of tool that's going to measure the energy per square meter. I don't know what the tool would look like, but whatever the reading is on there, it's going to convert as an output to decibels. So that formula would be like coded into the program. So just output the decibels for you. That's like with the football game where they have the little gauge there with the decibels in it, and they're like, oh, it's the sound of a jet taking off. You know, like, and the guy's like, I can't hear you, Paul.
Who are you imitating again?
I don't know. Can we just be having fun? Can it just be try to be fun?
I got you.
I'm trying to be fun.
It's hard when there's math going on.
I
I
know.
say math, this is not fun.
Well, we'll do our best to get as fun as we can. All right. Next situation, Richter scale. What do we use the Richter scale for?
Earthquakes.
Measuring the magnitude of earthquakes. Great. Our equation says R, that's the magnitude of our earthquake, is equal to log of A over T plus B. A is like the intensity of the earthquake, so that's like the amplitude, that's the amount of like distance displaced. So like if this is our two plates sitting together and they go like this, that value A is going to be the distance of the maximum distance it displaces. The T is the period, so that's the amount of time it takes for the plate to do this, and then return.
Oh, like on the squiggly.
Yeah, just like the sines and cosines from last semester, exactly right. So that's the amount of time. And then the B is a correction factor. Because the thing about earthquakes is no one knows where or when they're going to happen, right? So you're not going to have your tool to measure the earthquake sitting right at the earthquake epicenter.
That's why they have like more.
It's going to be some distance away. And what we've done is empirically, we've measured okay, how much does that signal that we measure decrease with distance?
Yeah, don't they have different
Yeah, they have different stations.
circles and where?
That's how they use to pinpoint where the epicenter was. Yep.
We did that.
Nice. So yeah, that's what B is. It's basically a correction factor. All right. So, example, the infamous San Francisco earthquake had a Richter scale magnitude of 7.5. How many more times severe was the most severe earthquake ever recorded? The 1960 Chilean earthquake that had a Richter scale magnitude of 9.5.
I think we learned about that one too.
Really?
Just a little, man.
So when we talk about the severity of an earthquake, what we're talking about is how much up and down the earth moved, right? That's the A. So if it's asking us for how much more intense was one earthquake than the other, you want that displacement from one earthquake divided by the displacement of the other. If that number is 2, then earthquake 2 was twice as strong as earthquake 1, right? So what we're going to be doing is solving for this A2 over A1. So we're going to write 2 sets of these equations. Because what we have given to us are the R's, right? So right away, I'm going to replace R1 with 7.5 and R2 with 9.5. So far, so good. Now, what can I say about the B's here? What is B again?
There's a constant that accounts for the weakening of the wave.
Right, so that's our little correction factor here. We only need the B if we're trying to calculate a magnitude, correct? If we already know the magnitude, we can assume the instrumentation to be at any location we'd like. What location would we like to assume our instrumentation is at? If we're able to pick where it would be at? Think about it practical standpoint. Where would be the best place to have your instrument? At the epicenter, which means the B would be 0. So that's what we're going to assume here. We're just going to assume the instrumentation is at the epicenter, so the B's are 0. Everybody cool with that? Okay. The T is the amount of time it takes for the plate to go up, down, back to center. Do you think that's going to be a long amount of time or a short amount of time? Probably short, right? None of us have probably been in an earthquake, but we've seen earthquakes happening on TV shows or movies or whatever. And when the earth is shaken, is it shaken slowly or quickly?
Very fast.
Really fast, right? That's kind of the destructive force of it. So that period is going to be really small. Everybody agree? So if T1 and T2 are both really small, what's the difference between them? Not a lot. So what we're going to do is we're just going to kind of assume that they're the same number, right? We're just going to assume they're the same. If they're not very big, if they're both not very big, the difference is negligible. We're just going to kind of assume they act the same way because it'll be close enough. Everybody cool? So I'm going to refer to this as equations A and B. If I do equation B minus equation A, we get 9.5 minus 7.5 is 2. We'll get log of A2 over T minus log of A1 over T. What can I do with this? Participation time. What am I able to do with that? I can't cancel. Because yes, that's one of our properties of logarithms. Do you remember which property of logarithms? It's the quotient property. Division is close enough. What does the quotient property allow us to do?
I have no idea.
It allows us to take that subtraction problem and rewrite it as a division problem inside the logarithm. What do you notice that I can do inside the logarithm there? I can cancel the t's. Good job. Now, really, what are we trying? We're trying to solve for a2 over a1. So we got to get rid of that log. What? Okay, so it is log 10 because there's no base written. What do I use to cancel out that log 10? What? Not log 10 to the other side. Not multiply by 10. It's exponent base 10. So we'd have 10 squared equals 10 to the log a2 over a1. So we get a2 over a1 equals 10 squared, or 100. So it was 100 times as intense, the earthquake in Chile, as it was in San Francisco. That's pretty rough, because that San Francisco earthquake was no picnic. You had freeways collapsing and stuff. I think that one was the one that happened during the World Series. There's a World Series game going on with the A's. The A's were playing somebody. I forget who they were playing. Yeah. It was wild. You had like your freeway overpasses collapsing and stuff. It was not a good day for San Francisco. And 100 times worse than that. Yikes. All right. Next situation is pH. What do we use pH to measure? Acidity of a solution. Yes, sir. We measure acidity on a scale from 0 to 14, where 0 is the most acidic and 14 is the most basic. 7 that lands right in the middle we consider neutral. That's also the pH of deionized water. All right. So that pH formula is equal to negative log of the concentration of hydrogen atoms. Or I should say ions. Our question says a real sour lemon is found to have a pH of 2.2, and a bottle of bleach is found to have a pH of 10.2. What are the hydrogen ion concentrations of the two items? All right, well, let's start with the lemon. So if I just plug this into the formula, 2.2, that's my pH, is equal to log of the hydrogen ion. I'm going to put a subscript of L on that so I remember that that's the one for the lemon. Participation. Well, what do I have to do to solve for that concentration of hydrogen ions? What should I do first? This is what I'm trying to get by itself, right?
Maybe this is more like LN.
Nope. That's okay.
What's the thing on the end?
That's just a subscript on it because we have to do this once for the lemon and once for the bleach. So I put an L on the end for lemon. I said it, but you were probably on your phone.
Is it probably like the same thing as the last problem? It's like times 10 on each side.
We'll need to use an exponent base of 10, but not yet. There's something we must do first.
Maybe they divide it by 1.
Not 1.
Oh,
Multiply by, oh wait, no, we're divided by 2.2.
Nope. not 2.2. We do need to divide by
Give
something.
a hint, like what, like between certain words. Oh, we divide the negative, so -1.
Yeah.
I think that is. You said by 1.
You said 1, man. Everybody heard
I
it.
knew in my head was the negative.
And then now we do that log base 10.
Now you do the log base 10. So you have 10 to the negative 2.2 moles per liter. Chemistry students, what's moles per liter also known as? Has another name, moles per liter.
Oh,
No, I don't remember.
It's molarity.
I've never heard that word in my life.
They use like the curly M. No?
That's where it's like electronegativity.
No, molarity is just moles per liter. We use it to measure concentration. There's two of them, two measurements you might use, molality and molarity. Molality is grams per liter. Now, if we do this the same thing for the bleach, the setup is like exactly the same, right? I'm just going to put a little subscript B for bleach.
Okay, so are we gonna know like all these like formulas for the test?
Do you think that you'd have to memorize these?
Well, I put it on the note card, but we don't know how to like use them.
You should know how to use them for sure.
Okay. So chemistry is
Yep.
makes a lot of sense.
Oh, this wasn't B though. Everybody's okay? I just did the exact same thing, so I skipped the work. Yeah or no? Yay?
No.
Okay. Part B then says how many times greater is the hydrogen ion concentration of the bleach than the lemon? I think that must be a typo because the lemon certainly has more ions than the bleach. So if I reduce 10 to the negative 2.2 over 10 to the negative 10.2, what do I get? We've done this all once already.
I believe it'd be whatever
It's like 10 to the 8. That's a big number.
10 to the 8.
I got that.
So like, what's that?
10 million,
I know, I think it's 100 million.
Yeah, it's 100 million.
100 million times more ions in the lemon than the bleach.
It's a big number.
It's a lot of ions. How they fit them all in there, I don't know. That's a joke. Yes, after I'm done. The next situation is for cooling objects. So like, how many of you guys have those pizza rolls you make in the oven?
Oh yeah, man.
Yeah, you eat those. What happens when you take it out of the oven and you pop one in your mouth?
They're hot, really hot.
You burn the heck out of your mouth with like the lava cheese, right? What Newton's law of cooling is doing is it's describing how hot objects cool. So, you take your pizza rolls out, you set them on top of the stove, you let them wait, and then sometime later you eat it and it's always still too hot and it burns your mouth. I think it's a plan because then you can't really taste any of the rest of them, so you can't tell if they're gross or not. They're probably all gross, but our mouth is too burnt to taste them anymore. This is them trying to make jokes. Yeah, I appreciate the pity. So our formula T of T equals T sub m plus T naught minus Tm times e to the negative kt. T of T is the temperature at some future time T. So like if we're talking about our pizza rolls, we set them on top of the oven, we come back 5 minutes later, what temperature are they now? Still hot, right. T sub m is the temperature of the surroundings. So like in our pizza roll example, that'd be like the air temperature in your kitchen, like 68, 70 degrees, whatever. So another situation, like imagine you're like a medieval blacksmith and you're like, you know, you take your sword, you pound on it, and you stick it in the cold water to anneal it, right? Like the temperature of the water then would be like the temperature of the surroundings. The E is that number 2.71, that irrational number we talked about earlier. K is a constant, but the constant is specific to the substance. So if we're talking about a medieval sword, the K for a steel sword is going to be different than the K for a pizza roll, right? The K is specific to the substance. And then T is time, traditionally measured in minutes. Sure. All right, our example, a hard-boiled egg is heated to 96 degrees Celsius, is placed in a pot of 16 degrees Celsius to cool. After 4 minutes, the temperature of the egg is 45 degrees. How long will it take to cool the egg to a temperature of 20 degrees? All right, let's go through this. Hard-boiled egg is heated to 96 degrees. What's 96? Which one of those is that? T naught. It's the initial temperature, right? That's how hot we heated it to. It's where it started at. What's the 16 then? That's TM. That's the pot of cold water we dropped our egg in to cool it off. It says after 4 minutes, well, that tells me T is 4. The temperature of the egg is 45. So 45 must be like T of 4, right? The temperature 4 minutes later. How long, well, there it's asking us to solve for T, will it take for the egg to cool to 20 degrees? So that's a T of T also. Look through what we've written down and compare that to the formula. Is there anything in the formula that we are not given? Is there any input to that formula that we weren't given in our story problem? K. So the first step is going to be using this information, the time and the temperature, to solve for K. And then once we have an answer for K, we can use that then to solve for T. Everybody cool with that plan? So a two-stepper. So plugging in, T of T is 40, or T of 4 is 45, TM is 16, T naught is 96, and then minus TM, that's another 16, e to the negative k, and then our time was 4. So we want to solve this equation for for k. How are we going to do that? Participation time.
Subtract 16.
Okay, so we can solve it directly. We subtract 16 from both sides. Then what?
Divide by 8.
Yes, that would be good. Okay, take the natural log of both sides. We don't say times because that'd be like times by square root symbol. But that doesn't make much sense. But you had the right idea. Yeah. That's good. Very good. What other way have we talked about how to solve an equation like this? So you can do it algebraically like Nick just walked us through, which is great. What's the other way to do this, though? That's okay. You did a great job telling us how to do it algebraically. Does anyone else remember how to do this not algebraically?
But if you like put it in like the y equals calculator, and then you just hit that point.
Yeah, graphically would be the other way of doing it. Yep, that's exactly right. So to run through how to do that, I'll put 45 into y1. That's one side of my equation, and then 16 plus 80 times e to the negative 4x instead of k. Everybody sound good? So far, so good? Now I'm going to set a window. X is representing k. I have no idea what x or what k would look like, but I'm pretty sure it has to be a positive number. And I'm just going to go 0 to 10 and take my guesses. Everybody all right there? The y, though, is representing the temperature. What's the coldest that this egg would ever be able to get? Not 0. That would be crazy. It'd be breaking thermodynamics. How about 16? Right? Like that's the cold water you drop the egg into. If it got colder than its surroundings, boy, that's destroying entropy. That's a problem, right? Now, if you put a 0 there, would it have been a problem? No, not. It wouldn't have mattered, but gives us a chance to talk about entropy, man. Like, I'm going to take that. What's the hottest this egg's ever going to be? There is a right answer to this. To the hottest the egg will ever be. Not 45. 96. Right? That's the temperature it came out of the pot of water, the boiling pot of water. It's okay. Again, it just needs to be bigger than what number? It doesn't necessarily have to be 96, but it needs to be bigger than 45. Had to be bigger than 40. So you can see the line y equals 45, right? Because we're looking for an intersection. If you couldn't see y equals 45, you couldn't see the intersection. But there it is right there. So I do second, trace, intersect command, enter, enter, enter. And there's my 0.254 again. Everybody happy? Okay. So once I have this now, I can write a new equation where 20 is my new t of t. And the k we now know is 0.254. And we're solving for t. So again, we could do what Nick had suggested and do it algebraically, which is fine. Or you can just type it into your calculator and do it again. Let's do that. Now I'm going to change my window because now x is representing time, right? I don't know, obviously 0 is the minimum for time. I know it can't, time can never be negative. The max I know has to be at least 4 because it took 4 minutes to get to 45 degrees and that's still well hotter than 20. But I don't know how long that's going to be. Maybe 20, 30 minutes is a decent upper bound guess. I always go for bigger than I think I need, so I'm going to put a 30 there. Anybody ever do or cook hard-boiled eggs? Takes them a minute to cool down in that cold water. If you put them in your refrigerator, some people do that. But here we go. There's my intersection right there. That's what I'm looking for. Second trace, intersect command, enter, enter, enter. You get about 11.8. Feel good? Okay. That's it for 15.4. 15.5, we're going to start today, and we're going to start by talking about interest rates. 15.5 is all about financial mathematics, so it's all going to be like banking or investment kind of related situations. So again, just more application. So that we're going to, yes, of course. We're going to start by talking about simple interest. Nobody really does simple interest. It's not really like a thing. Maybe your like illegal bookie uses simple interest because like it's easy, but like financial institutions don't do this. But simple interest is the interest is based only on the initial investment. So like if you invest $100 at 5% over 3 years, the first year you get paid $5 in interest, 5% of 100. The second year, you get paid still $5, 5% of 100. Third year, get paid $5, just 5% of 100. So you ended up making $15 over the course of 3 years. Everybody okay with that idea? So our formula described this, FV is equal to PV times 1 plus RN over 100. FV just stands for future value. What will the account be worth in the future? PV is your initial investment. That's our principal. That's the present value. R is the interest rate as a percentage. And N is the number of years, or like the number of times that interest is paid over this over the time frame. So example says if you invest $2,000 at a 6% interest rate, how much money do you have in the account after 3 years? Well, $2,000 is your present value. 6% is your R. How much total money do you have is your future value. And then 3 years, that's our N. Everybody's cool how I plugged in the numbers? You guys are so responsive all of a sudden. So I do that, I get 2360. So how much money did I actually earn in interest over that 3 years? $360. How'd you get the 360? Subtracted the initial investment from that final value, and you're done, right? No big deal. Everybody cool? The other way interest can be calculated is using compound interest. That's where instead of the interest payment being based on your initial investment, it's based on the current value of the account. So again, $100, 5%, but this time compounded. So the first year paid $5 because the account was worth $100 at the end of that year. The next year you're going to get paid 5% of $105. So like, I don't know, like not very much, but a little bit more. At the end of 3 years, you'll get 5% of the next value of the account. So you keep getting a little bit more in interest every year. You guys see that? Now, do you think this is going to make a big difference, little difference? Big. The answer is it depends. So our formula, FV is equal to PV times 1 plus R over 100K to the KN. The new parameter here is the K. The K is just the number of compounds per year. So again, if it's compounding annually, just one. How much total money? That's present value. And our N is 3. So I do that. And I have 238203. Why am I rounding to 2 decimal places? Yeah, because it's money, man. So how much better was this than simple interest? $22 or something. And at this point, you're going with school like, whoop-diddy-doo. Well, let's compare this. Let's say instead of doing this for 3 years, we did it for 300 years. Oh, Boise. Where did my guy go? There he goes. Everybody okay with that? So let's just pretend we did this for 300 years. Gosh darn it. So 38,000 on simple interest. But check this crap out. So you made 38K, or you had $38,000 using simple interest after 300 years. Compound interest, 7.8 times 10 to the 10th. That's like $78 billion. Which one would you rather have? I'll take that 78 billion over the 300 or the 38K, right? Yeah. So the moral of the story, over short term, not a whole lot of difference between simple and compound interest. Over the long term, massive difference. Compound interest is way better over the long term. Okay. Let's see, go back to where I was. All right, so we did that. So the K in these story problems is almost always going to be given to you in words. So just to run through, if we say something is annual, K is 1. Semi-annual, K is 2. Quarterly, K is 4. Monthly, K is 12. Weekly, K is 52. Daily, K is 365. Everybody's okay? And those are rounded, like 52 is not exact. There's like some days left over after 52 weeks. We don't care. Daily, there's a leap year. We don't care. Right? Like you don't have to be that precise. All right. So suppose Gina invests $800 at 7% annual interest rate. How much will she have in her account after 5 years if the interest is compounded annually, semi-annually, quarterly, monthly, daily, weekly, etc.? Okay. Well, let's get this in our calculator. We're just going to do this all on our calc and just update this each time. Sound good to you guys?
Put the times 1 on top.
Well, it's because the first one is annual. So annual is just once per year, so the K is 1. And because I'm going to change it each time, I just wanted to put the times 1 in there because it's easier so I don't have to add stuff later on. It's just me planning ahead. So $1,122 and some pennies, right? Now let's change that K to be 2. Do you think it's going to make, are we going to get more money or less money than $100 or $1,122? More. How much more? What do you think? Like $10, $20, $100, 7 cents? Like 100 probably. Okay, let's check. $6.40. Not a whole lot. If I change that now to quarterly, so I'm going to change the case to 4. Again, it's going to be more than the 1,128. How much more do you think, though? $20? Okay, let's check. And $3. What are you noticing each time here so far?
6 and then it was 3, so it's going to half each time.
Yeah, it's getting better, but not by much, right? In fact, it's a little bit less each time. So if I do this 12, picked up like 2 and some change, really, right? It was already almost 32. Okay. If I change that now to, what are we at? Weekly is 52. Come on there. Just some 80 cents or something. Yeah, just about. Anyway, it's like close enough for government work anyways. Oops. 65. And then here, like going from 52 to 365 is 30 cents, not even a quarter, less than a quarter. What's the takeaway?
It gets less each time.
Yeah, the K is not like, obviously the bigger the K, the better, but it's not like a very big difference maker. I'd much rather have a better interest rate or more time are going to be much stronger impacts than your K. But again, bigger K better, but it's like it's not an incredible push. All right, I think we have 2 more examples. Yeah, and we're gonna call her quits for today. Sound good to you guys? Sounds pretty good to me. Mara has $1,000 and places it into a savings account with 6% annual interest compounded monthly. How long will it take Mara to have $4,000? Is this simple interest or compound interest? Good. How'd you tell? Said compounded. Great. So the $1,000 is what variable in the formula? Yeah, that's the PV. And the 6% interest is? That's the R. What does monthly tell us? K is 12. How long? That means T. And then have 4,000. Well, that's going to be our future value, right? So we write our equation. Oops. I wrote 2,000. That's just supposed to be 1,000. All right. To solve this, what do we want to do? Okay. To solve this, what do you guys want to do? Participation. Well, let's just graph this, right? You could solve it algebraically and use a logarithm or whatever. Let's just graph and find the intersection. So to do that, into y1, what am I going to type? 4,000. Great job. And into y2, what am I going to type? The other side, right? All that other stuff. Okay. So in here, y1 is 4,000. So the y's are representing the money. And we put x where the t was, so the x is representing the time. So if I go pick my window, x is time, so it's a good x min. Participation. If x is time, what's a good x min? 0. Excellent. The x max could be, what's a good upper bound here? You think 69? You're a goofball. But like a bunch of time, 50 years, something, I don't know. We don't really know. It's a guess. I'd rather guess too high than too low. So whatever you think the answer might be around, maybe double it. You know, like I'd rather just do it once and have a squish graph than have to go back and change my window and make the x bigger because I can't see the intersection. The y's are the dollars. What's the least amount of money we'll ever have? Yeah, whatever the initial is. That's 1,000 in this case. And what do we need to have more than? 4,000. So what do you want to put there? How about 5,000? 4,001 is fine, but that's a smart alecky answer. All right, so I hit graph. Here's my line for 4,000. Here's my curve for the exponential. Second trace, intersect command. Oh boy. All right, try that again. Second trace, intersect command, enter, enter, enter. So 23.2 years. Does that sound okay? All right. Next question says, Gwen has $600 to place in a savings account. What annual interest rate would she need compounded weekly if she wanted to have exactly $1,500 in 10 years? So it's compounded. Yep. What is the 600? Yep, that's the PV. says what annual interest rate? So we're looking to solve for R. What's the K? 52. 52 weeks in a year, right? The 1500 is the future value and the 10 is the T. Oh my goodness, guys. We'll chalk it up to being, 2 o'clock on a Friday, right? Okay. All right. To solve this, how do you want to do it? You could solve it algebraically. To do this, solving this algebraically, you don't use a logarithm, though, because look at where the variable's at. It's inside the parenthesis rather than in the exponent. What are we going to need to use to solve this one? A 520th root to cancel the exponent of 520. Or, what else could we do? Graph it and find the intersection. Let's do that. Again, it's okay to solve these algebraically if you'd like. I do not need you to do that, though. If you want to just set it up and then graph it, that is okay by me. Okay. Change our window. X now is representing the interest rate. So again, 0 is obviously the minimum interest rate this could possibly be. You're not going to have a negative interest rate. That's bonkers. The max, I don't know, I'm going to pick 20%. That seems like a crazy high interest rate. Nobody's really going to ever get a 20% anything. But again, I want to overshoot whatever I'm going to do. The minimum I have would have been the 600 I had to start. The maximum needs to be bigger than the 2K. Or bigger than the 1500, I'll pick 2K. And then let's hit graph and see what we get here. Okay, there we go. Second trace, intersect command, enter, enter, enter. 9.17. What do you guys think? No big deal, right? 131 through 146 is the next, or the start of the next problem set. Sunday is just 37 through 130. A lot of us have already done that, it seemed like. And the delta math. This 131 to 146 will be for the following Sunday. So for Sunday, it's just the 37 through 130. I say just, like that's not very many problems. But it seems like many of us had already done that or got a big start on that. And then the delta math are the two things due this Sunday. This will be part of a problem set due the following Sunday. All that stuff should already be in my Notre Dame. Any questions about anything about what's due when or any of that jazz? Don't do that. You've answered like so many questions correctly already today.
It's like an AP exam like 2 days before.
Well, at least it's before and it's out of the way then.
Probably could be